Hello, everyone. I'm going to give you a quick recap and overview of Faraday's law for Physics 482. And the idea here is that this is after you've looked at lecture 16 and maybe before starting on lecture 17 on displacement current. I'm going to try and motivate that for you. So let's start. So to talk about Faraday's law, we have to define, or we first start thinking about motional EMF. And EMF is defined as this curly E, cursive E, and it's the loop integral of little f dot dl. Little f is the force per unit charge. So integral of f dot dl is the work per unit charge. And around a closed loop, we're imagining, for example, a loop of wire, and we're following a charge around that closed loop and seeing what the total work done around that closed loop is. And work around closed loop should remind you of something. It should remind you that the electric force is conservative, and therefore it can't do any work around a closed loop. And that's equivalent to the curl of E being 0 for electrostatic fields. And so that EMF integral reduces to an integral over all the non-electrostatic forces. We call that little f sub s for the source. So like in a classic battery circuit, right? If you have something like this, a battery connected to a resistor, the loop integral of the electric field is 0. That's Kirchhoff's loop law, that the sum of all the delta V's is 0 around the loop. But the EMF comes exclusively from the battery. There is a force in the battery pushing charges from the negative to the positive plate, pushing positive charges from negative to positive. That's against the electric field, and that's what generates the EMF in this circuit. There's other ways to make an EMF, though. Anything that's not an electrostatic force could generate an EMF. And here we're going to talk about magnetic motional EMFs. So this comes from moving your loop of wire or a loop of whatever through a magnetic field that results in a force on those charges. So in the notes in lecture 16, you derived the flux rule in a very special case, so a rectangular loop and a constant field. So I'm going to sketch out what the general proof looks like. So suppose I have some loop, and that loop is moving. And all those vectors I just drew there are the velocity vectors of parts of the loop. And so this can be a loop that it's not necessarily rigid. It could be deforming, it could be translating, it could be stretching or shrinking or doing anything like that. So all the different parts of that loop have different velocity vectors. And so a little bit later in time, the dotted loop there is what it's going to look like. It's stretched a little bit, it's moved a little bit. And we've got a velocity vector v at each point. And so what's our EMF? Our EMF is a closed loop integral of v cross b dot dl. So v cross b is the magnetic force per unit charge. We don't have to worry about whatever electrostatic field there is because its loop integral is going to give us 0. I use a little bit of vector magic to rearrange that vector triple product into dl cross v dot b. That's just an identity. I didn't do anything special there. And dl cross v is a little bit special. If I look at this picture here, and I look at dl cross v, the magnitude of dl cross v is the area of that parallelogram, shaded in yellow there. And the direction of dl cross v is given by the right-hand rule. It's perpendicular to both those vectors, and therefore it's the surface normal of that little patch of area. And so dl cross v is telling us something about the area of that surface, dA, except it's not really an area, it's an area divided by dt, because v is dx dt. And so that side of the loop is really dx, and so the whole area that I'm integrating is dA over dt. So that means my loop integral becomes really an area integral over a strip. And that strip is this shaded strip between the old and the new loops. So I'm doing an area integral over an infinitesimal strip. Then I'm dividing that infinitesimal area integral by dt. that area integral really comes from my original flux minus my new flux. Each of those is a surface integral over a different surface, and the difference of those two surfaces is the strip that I'm integrating over. You have to be a little bit careful with the sign, but at the end of the day, I get minus d flux dt, and that's a general result. Does not depend on the loop being rigid. It does not depend on the magnetic field being constant in space. Okay, so that derives the flux rule, and the flux rule came exclusively from magnetic forces. It came from the Lorentz force law and nothing else. So we haven't had to modify any of Maxwell's equations, but we can't leave it at that. And what we have to do is we have to think a little bit about relativity. And this is just Galilean relativity for now. So imagine moving a loop of wire past a bar magnet. As I move the loop through the magnetic field, the flux through that loop is changing, so I'm going to induce an EMF. But let me just change my frame of reference. What if I go to the reference frame that moves along with the loop? Then I have a bar magnet moving under that stationary loop. But those are equivalent. That's just the same system viewed in two different frames of reference, which means the same thing has to happen. The outcomes can't be different. So I have to have a non-zero EMF in both. That EMF is going to induce a current, perhaps. It may or may not induce a current, depending on the resistance of the loop. But something's got to happen in both. So on the right picture, though, every single charge in that loop, at least at first, is stationary. Velocity of each of those charges equals 0. So there cannot be any magnetic force. So it can't be V cross V that I'm integrating to get the EMF. The only other possible force on those charges is electric. But when I integrate the electric field around a closed loop, I'm supposed to get 0. And apparently that can no longer be true. When I integrate the electric field around this closed loop, I have to get something that's not 0. That tells me that the curl of E must not be 0 anymore. So how are we going to derive Faraday's law? I'm going to guess that the flux rule, the EMF, is equal to minus d flux dt. This is EMF. And this is minus d flux dt. I'm going to assume that this holds, even if it's not a magnetostatic problem anymore. I'm going to assume that this is still true. Then I'm going to use Stokes' theorem on the left. And on the right, I'll just move that derivative to the inside. I can do that because my surface, S, is constant in time. I'm not moving my loop. Therefore, I'm integrating over the same surface at different values of t. That means t can come through the integral, and I'm left with a partial b partial t in my flux integral. And then our usual trick is that it didn't really matter what my loop was. It didn't matter what surface I integrated over. So S was arbitrary, and therefore the integrands are equal. The curl of E has to equal minus the partial derivative of B with respect to time. And in fact, that's not 0 if my magnet is moving. So that solves our contradiction and gives us Faraday's law. So that's where it comes from. That's why it is what it is. You worked through a couple of applications of it on lecture 16. So what's next? What we have now, I'll give you the updated Maxwell's equation so far. The divergence of V is minus rho over epsilon naught. That's Gauss's law. The curl of V is now minus dB dt. That gold term is our new non-electrostatic condition. It's not curl equals 0 anymore in electrodynamics. Divergence of B is still 0. There's still no magnetic monopoles that we found. And the curl of B is mu naught J. That's Ampere's law. We haven't had a reason to change that equation yet. We started with the curl of B. We knew that was not 0 to start with. But there's something that we should check. The divergence of E and the divergence of B are scalar equations. Those are both trivial to satisfy. There's nothing special about those equations. But when I have an equation involving the curl is not arbitrary. I can't just have any vector field that's a curl, because every curl has zero divergence. So if I take the divergence of Faraday's law, the divergence of the curl of E has to be zero. On the right-hand side, I get divergence of minus dB dt. I can swap those derivatives because they're all partial derivatives. So to get minus d by dt of the divergence of B. But my other Gauss's law equation, the fact that there are no magnetic monopoles tells me that div B is zero. And so both sides of this equation are zero once I take the divergence. So nothing's wrong there. Everything's all good. Ampere's law is a problem. I take the divergence of the curl of B, I have to get zero, but the right-hand side of that gives me mu naught div J. And when we talked about the continuity equation and the conservation of charge, we know that divergence of J is not equal to zero if the charge density is not constant. If I have charge accumulating or leaving a particular place, the charge density at a particular place is changing, then J has some divergence there. There has to be a net current leaving a small surface around that point. That means that Ampere's law is inconsistent when charge densities are changing. I have to fix that. And so that's the subject of lecture 17 on displacement current. You're going to figure out what the correction to Ampere's law has to be in order to make it mathematically consistent.